Welcome to our excellent series on trigonometric identities. This is for the beginners who want to learn from the basics and master the skills of proving trigonometric identities. Let us enjoy the journey with Anil Kumar. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. Let me thank all the viewers and subscribers for watching my videos and taking a lot of interest. Because of you, we have thousands of videos on just one topic like trigonometric identities. Now what we are going to do here is make a concise playlist. We'll cover trigonometric identities in 5 parts. Here's part 1 for you. And in our 5 videos of trigonometric identities, you will learn everything you need to know about trigonometric identities, right from basics to what is trigonometric ratios and how they are related to compound angles. So let's begin with the very first one, part 1. We'll talk about skills and concepts you need to know to begin with. Then we'll take up these identities and prove them one by one. Quotient identity, Pythagorean identity, reciprocal identity. We'll also understand what do we mean by proof by contradiction and also take up counterexample concept. Now all these concepts are very important when we talk about trigonometric identities to begin with, right? In next video, which is part 2, we will take up proof of trigonometric identities with many examples. When I say many, it will be like 25 or 30. Okay. Now let's get to the basics. Now here is a quick review. You really know what trigonometric ratios are. Trigonometric ratios are defined as sine, cosine, and tangent ratios. These are the primary trigonometric ratios. And when I say sine is opposite over hypotenuse, that is my way of writing SOHCAHTOA over. So really, here what I really mean is, let's look into this. It means sine ratio is opposite over hypotenuse as shown in this particular diagram, and means that sine theta is equal to opposite side over hypotenuse. Is that clear to you? So that is how we will define all of the ratios, as you know. And then here we have a coordinate system. In the coordinate system, you know, this is the quadrant 1, 2, 3, and 4. All are positive in quadrant 4. Sine is positive in quadrant 2, tan in 3, and in 4. Only cosine is positive. When we talk about quadrants, we know any point here will have a value which is both x and y are positive. And that is why all are positive in quadrant 1. In this case, the x value is negative, but y is positive, and therefore sine is positive. And here we know both are negative, so the ratio of sine and cosine, which is tangent, is positive. And in this case, we have x value as positive, but y as negative. And that is the reason why cosine is positive in quadrant 4, right? Most of the things are known to you. Now we'll also consider a point on a terminal arm. This is whenever we talk about an angle and we say principal angle, we mean that the vertex is at the origin, the initial arm is along the x-axis, and that's the terminal arm. We take up a point on this terminal arm, which I will be writing AB. That means a specific point which I am showing there. However, remember that A belongs to all real numbers and B also belongs to all real numbers. So in general, we can write this point as xy, right? Do you see that? So I may be writing A and B just to show you that particular point. However, we're trying to say in general that this point could be anywhere, right? So it has generally value x and y. If the point is in quadrant 1, you can see both A and B will be positive. If it is in quadrant 2, A will be negative, but B will be positive. So that is how you have to correlate. Perfect? Okay. Now, as I was saying, we also sometimes use a circle to just show you where what is positive. Now in this circle, I've taken a point P, which is X and Y. So that's general, right? Now if you drop a perpendicular from any point to the x-axis, that becomes the side which is opposite, right? So PQ is the perpendicular. You will see that sine theta is basically equal to PQ over OP, right? OP. And then we can see what is PQ. Well, PQ is basically the value of Y value, correct? And OP is the R value. This R value can be calculated using x square plus y square square root. So it's a constant with a positive value, always positive. So OP is R. So in that case, you can write y as equal to r times sine theta. You see that? So basically, any point xy on a coordinate system can be represented in terms of sine and cosine, correct? So remember this, that if I have a point xy on a coordinate system, it could be treated as r cos theta. That is the adjacent side, right? So x value will be r cos theta and the y value will be r sine theta. Very important concept to understand, right? So sine theta is basically y over r, and so cos theta will be x over r, correct? That is how you have to relate them. Once you understand this, we'll actually prove the trigonometric identities, which are like Pythagorean identity and all those which we have been talking about, with the help of just this concept. So this concept is extremely important to understand. So I hope this is absolutely clear, right? So are you ready to move forward? Perfect. So here is the very first question for you. After all, what is an equation and what is an identity? Well, we know identity is also an equation, right? So we write equal to sign, that means it is an equation. Perfect. Now let's look into what is an equation and what is an identity. So I have 4 sets of equations here for you. I'd like you to take a moment, watch carefully these 4 sets. First one, set A, 2x minus 1 equals to 5. Now this set has only one solution, and the solution you know will be what? You will add 1 to 5, right? 6 divided by 2, so we get x equals to 3, correct? So this equation has one solution, perfect. Now this equation, which is in the quadratic form, we know for this to be true, x has to be minus 3 or 1. Both can make it true, right? Perfect. So we have one solution, we have 2 solutions. So we have some solutions in this case. Limited number of solutions. That is what I'm trying to say. Now set B. X plus y equals to 0. It means that what is y equals to? Well, y is equal to any value of x, right? Minus of x. You could write either way, right? Now that means what? That means that this equation has infinite solutions, right? You know this line on a coordinate system, y equals to minus x will be a line which will be diagonally going downwards like this. So we know we have infinite solutions. Do you see that? Okay. Now next one. X square equals to minus 1. Well, square means it has to be positive, right? So in this particular case, we have no solution. Amazing. All our equations, mind it, all our equations, but the first set have limited number of solutions. The second set has either unlimited solutions or no solution, right? Perfect. Now let's look into set C and D. What do you think is the difference between set C and D and set AB, which we just talked about? Well, here we have written 3p plus 5p is 8p. Now here, p could be anything. We know 3 plus 5 is 8. So this is always true. You see that? So we find that this is always true. Means you could put any value of p, it will be true. How about this? X square minus y square equals to x plus y times x minus y. Well, again, any value of x and y you choose, it doesn't matter which x and which y. So you see the difference between this and x plus y equation? I could put x as 5, y as 7, whatever, right? This equation will be true. You get the idea. But in the first case, if I have to put x as 5, y will be minus 5. You get the idea? Y gets limited. Here both have infinite values. And it is always true. You get the idea. Now the last one here, you will learn soon. Sine square theta plus cos square theta equals to 1. This is always true. It is called a basic trigonometric identity. Since it is derived from like Pythagorean theorem, we always say this has to be Pythagorean trigonometric identity. And this ratio, sine theta over cos theta is tan theta, you already know is always true. So what do you conclude from here, right? So we conclude that an equation could have a solution, could have many solutions, may not have a solution. That is an equation. But what is an identity? Well, these two sets belong to an identity, right? They represent identities. So identities means always true. And of course, denominator cannot be 0, right? So we know denominator cannot be 0. Not equal to 0. Perfect. Because that point is not in the domain. So those will be the restrictions. Perfect. So whatever numbers make the denominator 0 will not be part of this always true, right? Perfect. So we don't keep writing, well, theta is not equal to this. We know that this is a restriction on any rational type of an equation, or wherever we have a denominator, we cannot divide by 0. Correct. So that is what we have here. Now, trigonometric identity means we have trigonometric ratios involved. Then it becomes a trigonometric identity. So, trig identity, let me write it short. Trig identity is an identity which have trig ratio. At least one. Is it clear to you? At least one. So that is what trigonometric identity is. So I hope this concept, what is an equation and what is an identity? Identity is an equation which is true for all values of its independent variable. In its domain, I am adding that part because the denominator cannot be 0, right? So those values which are not in the domain should not be considered. Perfect? So I hope this is clear to you, right? Let's move forward and see what do we have. So, yes, now we have learned that equations may or may not have solutions, correct? But identities are equations that are always true. That is basic summary of what we just learned. Now let's talk about how do we prove these identities. So just now I was saying that tan theta is basically a ratio of sine and cosine. We call this as a quotient identity. So what is quotient identity? Quotient identity is tan theta equals to ratio of sine and cosine, right? So we'll now prove that tan theta is equal to the ratio of sine theta over cos theta. Now one of the best ways to prove it is looking at the coordinate plane itself. So what I'm doing here is taking a point AB on a coordinate plane. So if I have a point AB, then R, the distance from the origin to the point P, will be what? R is going to be A square plus B square square root, right? It will be positive, always right. So here what is sine theta? Well, sine theta is the ratio of opposite to hypotenuse. So if I drop a perpendicular here, as you can see, then sine is the ratio of this opposite side, which is basically of length B, right? So B over R. Hypotenuse is R. Is that clear to you? Cos theta is the ratio of adjacent side, which is A over R. So how do we prove that tan theta is sine theta over cos theta? Okay, let's go like this. We know what is tan theta, right? So tan theta is what? let me use a different ink. Tan theta in this particular triangle will be opposite side over adjacent. That is B over A, right? No problem. Tan theta is B over A. Now, how about dividing both numerator and denominator by R? I could write this as B divided by R over A divided by R. Is that clear to you? Now, what is B divided by R? Well, B divided by R is sin theta and A divided by R is cos theta. You get the idea. So, we can write down this as sin theta over cos theta. Makes sense? So, that is how we can prove this quotient identity. Is that clear to you, right? So, here is the proof for you. So, we know if I divide sin theta by cos theta, sin theta is B over R, cos is A over R. R and R cancel, right? So, you get B over A and that is equal to tan theta. So, we could do the other way also, starting with either tan theta or starting with sin theta over cos theta. So, the concept which we are learning here is this. We learned that tan theta is equal to sin theta over cos theta, right? We know this is an identity. So, what you could do is you can start with the left hand side, right, as we did first, and then show that this is equal to right hand side, right? Or you could start with the right hand side and show that that is equal to the left hand side. Either way, you show it. Sometimes we may be proving identities by simplifying both left side and right side if things are very complicated and showing that they are same thing. So that becomes a standard way of proving an identity. So our first proof on quotient identity actually provides us with a method of proving identities. Is that part clear to you? Perfect. Okay. So simple things teach us a lot. So we have to appreciate as we move along. Right. So next, I'd like you to now prove that cosecant theta is 1 over sin theta. Well, to prove this, again, you can take this coordinate system, correct? So I'm giving you a moment to just prove it. Cosecant theta is 1 over sin theta. So you can use this point AB, which I am saying in general. What we could do here is also take a general point, right? So let's take any general point and let's call this point as xy, right? I'm calling this now as xy. In that case, from the origin, the distance will be r, correct? And if I drop a perpendicular from xy, and this is my principal angle theta, in that case, you know that from O to P, we have r, and from O to Q, the perpendicular drawn, this distance is x and that is y, correct? Now, what is cosecant theta? Cosecant theta basically is ratio of, see, sine is the ratio of opposite to hypotenuse. Cosecant is ratio of hypotenuse to the opposite side, correct? So, in this case, hypotenuse is r and the opposite side is y, correct? Now, what we can do is we can divide by r in both numerator and denominator. So, what do we get? We get 1 over y over r. And that is what? Well, that is clearly 1 over sin theta. Because sin theta is the ratio of y over r. And that is how we have shown that cosecant theta is 1 over sin theta. Do you see that? So, we began with the left hand side and we showed the right hand side is 1 over sin theta. Well, you could begin from here, you know what sin theta is, and prove the left hand side. So, either way, you can work while proving the identity. So, I hope you are getting this concept of starting with left hand side, getting to the right, or starting with right hand side, getting to the right. Okay. So, anyway, we just proved this, that in this particular case, if we start with the left hand side, which is r over b, we can actually divide by r, so get 1 over b over r, which is 1 over sin theta, correct? I like you to prove this identity from right to left also. That gives you kind of confidence of working with these identities and how do we prove them. So we have done this quotient identity. Now let's look into proving the trigonometric identity. Now this is very basic and most important identity, and I'll provide you with one of the simplest proof, right? So again, we could take this point AB on the coordinate plane. As I have been saying, A and B is any general point, right? So I will now extend this to any general point xy, right? So I could have any point here, right? Not just AB, right? We have any point on the coordinate plane xy with a distance r, correct? So where r is equal to square root of x square plus y square. You get the idea. Any point. So when we can prove something for any point, that means it becomes an identity true for any point in your Cartesian plane. Perfect? Makes sense, right? So making an angle theta, so we'll follow this diagram. However, we'll generalize the point. Instead of AB, we'll take x and y. Clear? So we know from Pythagorean theorem that x squared plus y squared is equal to what? Well, this is equal to the hypotenuse square, which is r in this case, right? So we get this statement. Now see what happens if I divide everything by r square. See how simple it is. I'm making it absolutely simple for you to understand. So as soon as I divide, I get x over r squares, right? Y over r, both squares. R square by r square, 1. Oh my God. What is x over r? X is the adjacent side. So we get this as cos square theta plus y over r is sine. So we get sine square theta. And r square by r square is 1. So we have cos square theta plus sine square theta is equal to 1, which can also be written as sine square theta plus cos square theta equals to 1. Makes sense? Correct? That's simple, right? If you follow this A and B, you can also prove that 1 plus tan square theta is secant square theta and 1 plus cotangent square theta is cosecant square theta. So simple as that. So you can pause the video at this particular stage and prove the other two trigonometric identity. So basically, these three, sine square theta plus cos square theta equals to 1, 1 plus tan square theta equals to secant square theta, and the third one here, which is 1 plus cotangent square theta is cosecant square theta, are the basic primary trigonometric identities, correct? Okay, so here is the proof of sine square theta plus cos square theta. We use the points A and B. I generalize them for you. Now, I like you to prove 1 plus tan square theta equals to secant square theta. Well, the concept is same. If I take x and y points, then we have x square plus y square equals to r square, correct? R square is the hypotenuse. If you want secant, you have to divide by adjacent side, which is x square, correct? So this time, let me divide by x square, correct? Makes sense, right? Making things absolutely easy for you. So what do we get? Well, we get 1 plus y over x is tan. So we get tan square theta equals to secant square theta. Easy. So that is how you just prove them, right? So you can prove 1 plus cot square theta is cosecant square theta. Also, just follow the same instruction. You have to divide by what? Well, divide by, simple as that, y square, correct? You will prove it. Perfect. So that is how we actually prove these identities. So you can see, here is the proof for 1 plus tan square theta, taking a point A and B where you know A belongs to, A and B both belongs to all real numbers, right? So we say A and B belongs to real numbers. So this is another way of writing. Perfect. Now, 1 plus cot square theta, also we'll do the same thing, which is what? X square plus y square equals to r square. And since we want cosecant square, we have to divide by what? Opposite side, which is y square, right? So just divide by y square and get your result. So your result will be what? 1 plus cot square theta equals to cosecant square theta, right? Simple as that. Now here is a question for you. Very, very important question. Now the question here is the following an identity? Is the following an identity? Cot theta is square root of cosecant square theta minus 1. True or false? Yes or no, right? That's your question. Can you please tell me this? Well, let me be very clear about it. It is not an identity. Now, can you tell me why? After all, we have 1 plus cot square theta equals to cosecant square theta, right? Why this is not an identity? Let's also look into this as it is a common mistake. So 1 plus cot square theta is equals to cosecant square theta. We can isolate cos squared theta, right? Of course we can. And we can write this as cosecant square theta minus 1 and then take square root. So when you take square root, we get cot theta equals to what? We get square root of cosecant square theta minus 1, right? It looks like an identity. But now, when you take square root, you have to write positive and negative, right? As you can see in quadrants, you know the cast rule, right? Cotangent is positive in only quadrant 1 and 3, right? Not in quadrant 2 and 4. So, if you write like this, it seems as if cotangent is always positive, but it has a negative value, right? Especially when you have an obtuse angle, perfect, right? Or a negative angle, right? Like this. So, be careful about this. So, here we have actually shown you that what is not an identity. Sometimes they may look like an identity, but they are not. So, we may have to prove that this is not an identity, or sometimes identify whether this is an identity or not, correct? So, here is the proof for the cot square theta, the third Pythagorean identity. Now, here is another very popular question on identities, right? So, this is part 1. We have learned what the identities are with which we will be working. Quotient and Pythagorean identities are the basic identities which will be utilized even in our part 2 and part 3 to prove all the identities. Perfect. Now let's see two more concepts. One concept is prove or disprove or contradict, right? So here is a statement. Cos x is equals to square root of 1 minus sine square x is an identity. So is it true or it is not true? Well, one way is as we did for cotangent, you remember. Other thing is the concept of contradiction. As I told you, identity is always true. So if I take a value for which this is not true, I have shown that this statement is incorrect. You get the idea, right? This statement is incorrect. So let's take an angle. So let us say if x is equal to 120 degrees, let us say x is equal to 120 degrees. In that case, we are talking about an angle which is having an acute angle of 60 degrees, right? 120 degrees is this, correct? So the remaining is 60. You can look into your triangle, which is 30, 60, 90, right? So 30, 60, 90 triangle. And you know what cos 60 is, right? So in this triangle, this is half, right? And square root 3. We're talking about this angle, 60 degrees. Since you are in quadrant 2, you also know the cast rule, correct? You know the cast rule. So in quadrant 2, what is positive? You know cos is positive in quadrant 1 and in quadrant 4. In 2 only sine, and in 3 tan is positive. So here for 120 degrees, what is the value of cos, right? So we have cos of 120 degrees is equal to negative half. Do you see that? Cos of 120 is negative. However, square root will be positive, right? Square root will be positive. So that shows which is not equal to square root of 1 minus. The value of sine square x will be square root 3 over 2, right? Square root 3 over 2 whole square, right? Because the right hand side is positive. You see that? Right hand side is positive half. The left hand side is minus half. And they are not true. Therefore, we have contradicted this statement just with one example. So, contradiction is a very, very powerful way of showing that this is not an identity. Perfect. So, even if the equation is not true for one value, it is not an identity. Is that clear to you? So, we can prove it easily using the method of contradiction. So, we contradicted these equations' validity. Perfect. So, that is how you do it. So, here is what I just showed you. So, in this case, it is not an identity since cos of 120 degrees is negative half. However, the right hand side will be positive. So, basic identity will be you have to write plus and minus. Do you see that? Or the identity is absolute value of cos x is equal to square root of 1 minus sine square. Does it make sense? Because then you'll make the left hand side as positive. So that is an identity. Do you see that? This is an identity. So if you make it absolute value, it is an identity. You get the idea. Perfect. Or sometimes we'll just write cot as plus minus cosecant square theta. That is an identity. Correct? So, but you'll have to think when is it plus, when is it minus. The better way to write this is absolute value of cotangent theta is equal to square root of cosecant square theta minus 1. Makes sense? Right? That is an identity. Better way of writing. Correct? So we have learned how do we prove that something is not an identity by contradiction. Extremely powerful way. Now here is another way of proving or disproving, and that is counter examples. Counter examples also, like we gave a counter example last time also, making the angle as 120 degrees. Now in this case, provide an counter example to show that sine A plus B equals to sine A plus sine B is not an identity. So in this case, what can you do? Just take a value of sine A and sine B. Let's say, if you say angle A is equal to, let us say 30 degrees, right? And angle B as equal to 60 degrees, correct? So in that case, what is A plus B? So A plus B will be 90 degrees. We have taken an example, right? So counter example really means take an example and then show that this is not true, right? So we can write what is sine of 90 degrees? Well, we get sine of 90 degrees here. And on the right hand side, we have sine of A is 30, right? And B is 60, sine of 60, correct? So if we calculate, what is sine of 90? Well, sine of 90 is 1, right? So let's write down what is sine of 90. Sine of 90, as we know, is 1. And what is sine of 30? Getting back to our triangle, if you don't remember these values, so that is a 60 degrees, sine is square root 3 over 2, and this is half, right? So this is half plus sine of 60 degrees is square root 3 over 2, right? And you know, half plus half is 1, not this. And since this is not true, we show with the help of a counter example that this is not an identity. Is that clear? So important to note is for identities, the equation is true for every real number in the domain of the function, right? Denominator cannot be 0. Counter example to show that the equation is not true for even one value is an effective way to answer at times. Perfect. To show that it is not an identity. Does make sense to you, right? So here is the calculation done for you. What exactly I was trying to show you. So sine 30 and cos sine 60, if you add these values, it is 1 plus square root 3 over 2. But sine 90 is actually 1. Since left side is not equal to the right side, it is not an identity. Perfect. So with that, we have come a long way understanding all these concepts, right? So I hope now you are ready with the basic skills required. You know what these trigonometric ratios are, how can they be related, and we have seen how do we prove quotient identity, Pythagorean identity, reciprocal identity. We have also learned the concept to prove or contradict a statement, which is a kind of an equation, right? And how to use counterexamples very effectively to show that this equation is not an identity. So with that, I think you're absolutely ready to take up hundreds of examples on trigonometric identities, which are coming up in part 2. Well, feel free to write a comment, share your views. That will help us improve our services. In case you want to learn from me directly, you can send the email to me on the given address. Also, you can contact us on our website for more details. Thank you and all the best.